Hi, my name is Samir Gadre from Columbia University. I am excited to present our work on learning to interact with articulated objects to discover and segment parts. Motivated by playfulness in kids, we ask the question, can we learn an agent to act intelligently and segment parts from interaction? To answer this question, we have to address several challenges. First, motion cannot be assumed in a scene. For example, these scissors won't move unless something interacts with them. Second, even with agent interaction, not all actions give insight about articulation. These actions rotate and translate the scissors rigidly. Third, actions might activate only a small number of parts each step, so diversity of actions and aggregation of discoveries is necessary. We would like to segment and track parts as they move. Finally, generalization of interactions and perception to unseen categories without retraining or fine-tuning is desirable. If we learn how to interact with scissors, we should be able to interact with eyeglasses too. Prior work cannot readily address all these challenges. In our work, Act the Part, we train a single agent to hold and push to isolate parts. The resulting motion cues make part discovery and mask recovery possible over a few time steps. In this example, we show our intended method should be able to discover both parts with smart interactions. Our key insight is to couple an interaction network for action selection and a part network for motion segmentation. Given the current observation and belief about the segmentation, the interaction network determines the hold and push action. The action is executed in a pi-bullet simulator, yielding the next observation, as well as ground truth optical flow. Our simulation environment supports partnet mobility style objects. The pair of observations and the action are passed to a part network that determines the mask of the part that moved. History aggregation updates belief about the segmentation. Let's take a closer look at action selection. We use a ResNet backbone with UNet-style decoders. We predict a hold map where each pixel gives the confidence of holding at that pixel. Notice areas that have already been segmented have higher hold affordances. A pixel is sampled from the distribution as the single hold location. To limit the action search space, we condition our push prediction on the hold location and consider 8 discrete push directions 45 degrees apart. We use a similar sampling procedure to choose a push location and direction. Hold and push maps are supervised using signals from optical flow, force feedback, and part mask history. For motion segmentation, we create a part network. Decoders predict two masks, the first of the moved part aligned to the current frame, and the second of the moved part aligned to the next frame. Masks are supervised using thresholded forward and backward optical flow. Finally, let's look at history aggregation. The current mask prediction is used as a query. We ask, does this mask overlap significantly with any part in the memory? If so, we need to update an existing part. In this case, there is no significant overlap, so we allocate a new channel for the next part mask prediction. Here are some sample instances from our train and test categories, from both partnet mobility and the real world. Test objects can have 3 links or deformable links, even though all train categories only have 2 rigid links. We show that our approach is able to find a high percentage of optimal actions where new parts are discovered. For more details and numerical analysis, please see the evaluation section of our paper. Now let's look at some qualitative results. We find our model is able to discover and segment all 3 parts on eyeglasses, which have more links than any instance seen during training. Surprisingly, the same model works on real-world data with no fine-tuning. A human operator executes actions on behalf of the model. Here are more results on real-world objects. Notice some objects have deformable structures, which were never seen during training. Our model is also able to reason about where to push based on arbitrary hold locations. We highlight this capability by visualizing push affordance maps for all 8 directions. As the hold changes, the push subnetwork is able to select sensible push locations and directions. Please see our project page, where you can select hold locations of your own to probe our model. Thank you for watching.